Jai to all. Today I am here to present the video lecture of subject control system BEC 602. This subject is running in 6th semester of AKTU curriculum, and the topic of my lecture is polar plot and Nyquist plot. So in this particular lecture I will cover the theory related with polar and Nyquist plot, concept behind that, and some problems by which students can better understand this concept of polar and Nyquist plot. So let us start. So introduction to polar plot. So if you have already seen this Bode plot, so the limitation of Bode plot is that it requires the presence of both magnitude and phase plot of a system with respect to change in the frequency. Means we require magnitude plot and phase plot to draw the frequency response of the system. But if we'll talk about this polar plot, then polar plot combines both magnitude plot and phase plot to a single plot without losing any information. So this polar plot consists of both magnitude and phase information simultaneously with respect to the frequency. The polar plot can either be plotted on a polar graph or on an ordinary graph. The polar plot of a loop transfer function, our loop transfer function is Gj omega Hj omega. For sinusoidal frequency analysis, we will put S equals to J omega in the given open loop transfer function. So magnitude is defined as magnitude of Gj omega Hj omega, and angle is defined as angle of Gj omega Hj omega on the polar coordinates, and we will vary the frequency from 0 to infinity, and then we will plot the graph on a polar graph. So it is a you can say a polar graph. So this is the first question which we can see here. The open loop transfer function is given as GSHS equals to 1 upon 1 plus T1s into 1 plus T2s. So for frequency domain transfer function, we will put S equals to J omega in this equation. So Gj omega will become 1 upon 1 plus T1 J omega into 1 plus T2 J omega. Then we will take the magnitude. So magnitude mod of Gj omega Hj omega, we can call it as M, and that will be equal to 1 upon, so 1 plus J omega magnitude means real part ka square plus imaginary part ka square. So similarly, this will become 1 plus T1 square omega square, and this term will become 1 plus T2 square omega square. And then we will write the angle. So angle of real part, you can write it like 1 plus J0 upon 1 plus J omega T1 to 1 plus J omega T2. So angle of this will become tan inverse imaginary part upon real part upon tan inverse omega T1 upon 1 into tan inverse omega T2 upon 1. So this comes out to be tan inverse 0, it is 0, and here you can write it is tan inverse omega T1 and it is tan inverse omega T2. So this comes out to be minus tan inverse omega T1 minus tan inverse omega T2. So this is our phase angle. Now what we will do, we will change basically the frequency from 0 to infinity and find out the value of magnitude and phase. So what we are doing here, we are not interested in each and every value of omega between 0 and infinity. We are just trying to find out the movement of the plot with respect to change in frequency. So let us just take our starting point as omega tends to 0 and terminating point as omega tends to infinity, and we will calculate the value of magnitude and phase angle at these frequencies only. So when omega equals to 0, it comes out to be, when you will put omega equals to 0 here, it will come out to be 1. So you can see the magnitude is 1. When omega tends to infinity, then you can see this will become 1 by infinity. It means angle is, it means magnitude is 0. Now we will check the angle according to this expression. When omega tends to be 0, then it is tan inverse 0 minus tan inverse 0. It means 0 degree. and when omega is in infinity, then it is tan inverse minus tan inverse infinity minus tan inverse infinity. It means minus 90 and minus 90, it comes out to be minus 180 degree. Now we will check the rotation. So how we will check the rotation? We will subtract terminating point angle. We will subtract the starting point angle from terminating point angle. It means it will become minus 180 minus 0 degree. It means minus 180 degree. So when angle comes out to be minus, then the rotation will be clockwise. It is important to note that when the angle is negative, we will move in clockwise direction, and when the angle is positive, we will move in the anti-clockwise direction. So from here, we will draw the polar plot, and first we will take the value 1. One value is this. It is on the positive real axis, and angle 0. This is the angle 0, and the magnitude 0, and angle is minus 180. So magnitude 0 is this point, and angle minus 180. This is also the minus 180 line. So this is the point of 0 minus 180. Now we have to go from this point to this point by making an angle of 180 degree. So this comes out to be like this. So this is basically our polar plot. Okay, so we can see this polar plot is entirely came into third and fourth quadrant. So this is how we will draw the polar plot. Now take the another example. You can see here there is no s power of s, or you can say power of s is 0. So this is a type 0 system. Now we will take a type 1 system. In type 1 system, in the denominator, power of s will become 1. So this is an example of type 1 system. Now we will draw the polar plot, and also we will find out the stability. And stability parameters are gain margin and phase margin. So we will see how we can calculate the values of gain margin and phase margin from with the help of polar plot. So now we will put s equals to j omega. This comes out to be 12 upon j omega times 1 plus j omega into 2 plus j omega. Again, we will calculate the magnitude. We will take the mod of a plus jb. That will become under root a plus b square, under root a square plus b square. Accordingly, we will write this equation: 12 upon omega under root 1 plus omega is under root 4 plus omega square. And angle, here again angle is 0 degree. According to this is a single pole. It will subtend an angle of minus 90 degree, or 90 degree in the denominator. So minus 90 in the numerator, you can say. So the angle comes out to be minus 90 minus tan inverse omega minus tan inverse omega by 2. Now again, we will put the value omega 0 to infinity. We will check the values of magnitude and phase angle from here. When omega equals to 0, according to this term, you will get the value of m as infinity. And when omega equals to infinity, as per this term, you will get magnitude equals to 0. Now, you will put the value of omega equals to 0 here. So you can see these values are 0. So angle is minus 90. And when omega tends to infinity, you will find minus 90 and minus 90 from here. So it will become minus 270. So now again, we will subtract minus 270 to minus 90. So it comes out to be minus of 180 degree. It means we have to move from here to here by making an angle of 180 degree in clockwise direction. Okay. As we are interested in finding out the stability, also gain margin and phase margin. So we will make the polar plot, but we are also interested that where this polar plot cuts the negative real axis. Okay. So you can see the polar plot. This is the polar plot. So we have drawn this polar plot on the exact graph paper so that the calculation of phase margin can be done easily. Okay. So you can see from here, if we will draw the rough polar plot, you can see the value is magnitude is minus 90 for omega equals to 0, minus 90 line will be this, and magnitude is somewhere here, you can say, and for infinity minus 270, this line is magnitude 0. So you can say it is 0 minus 270, and this is, you can say, point infinity minus 90. Okay. So we have to move from infinity minus 90. So we have to move from here to here by making angle of minus 180 degrees. So that's why this plot will comes out to be somewhat like this, somewhat like, more specifically, it will be somewhat, this is somewhat, like this. Okay, so this we have drawn over here, but this is the rough polar plot, and that is the polar plot drawn on the graph paper. So how we will calculate this point? What is the values of these points? So for this, we will rationalize the transfer function. So how we will rationalize the transfer function? Transfer function can be rationalized by multiplying the conjugate values. Okay, so we will take this term and we will multiply by the conjugate of this term. So you can see here j omega 1 plus j omega 2 plus j omega. So we will multiply by minus j omega 1 minus j omega 2 minus j omega in the numerator and denominator both. And then after multiplying, we will solve it and separate the real and imaginary part. Okay, and what we will do for calculating this frequency, where this polar plot cuts the negative real axis, this frequency is called phase crossover frequency. Phase crossover. Okay, so we will calculate the phase crossover frequency by putting this imaginary part equal to 0. So it will give you the phase crossover frequency. And then we are interested in this particular magnitude value. So how this magnitude is calculated? We will put this frequency value which we have obtained from here and put it into the real part. When we will put it into the real part, we will get this distance. Let us suppose this distance. Okay, so we will get the value of OQ. Okay, so this we have done. So we have put this 2 minus omega square equals to 0. So you can say omega PC will become root 2 or 1.414 radian per second. And then we will put this value into this term in the real part. When we will put this into real part, this value comes out to be minus 2. This value comes out to be minus 2. It means this value is the minus 2 where the polar plot cuts the negative real axis. Okay, and this gain margin in dB is simply 20 log length of 1 upon OQ, means this distance, 20 log 1 upon length of this distance. So it comes out to be minus 6.02 dB. So gain margin is negative. So you can say the system is unstable. We will also calculate the phase margin, and phase margin, basically phase margin is calculated at gain crossover frequency. Gain crossover frequency. Gain crossover frequency is the frequency at which the value of gain is 1, or this value is obtained by draw a unit circle of radius 1, draw a circle of radius 1 which cuts the polar plot at a point, and this frequency is nothing but the gain crossover frequency. And angle at this gain crossover frequency, when we will calculate, that will become phase margin. 180 of this angle, 180 plus phi. Let us suppose this angle is phi, so this will become, you can say this is basically the phase margin. So the phase margin comes out to be minus 17.5 degree in this particular case, because we are measuring in this direction. Okay, so phase margin is minus 75 degree, as both gain margin and phase margin are negative, hence the system is unstable. If the system is stable, then gain margin and phase margin both need to be positive. But in this case, because gain margin and phase margin both are negative, hence the system is unstable. Now come to the Nyquist Stability Criterion. What happened in case of polar plot? There are some situations, you can say, where the stability cannot be found easily because of conditional stability. So the cases wherein we are not able to find out the stability, we'll use the Nyquist Stability Criterion. The difference between Nyquist and polar plot is that polar plot is basically an open plot, and Nyquist plot is basically a closed plot. So through Nyquist analysis, we can also find out the stability of those transfer functions which cannot, for which stability cannot be defined using polar plots. So the Nyquist Stability Criterion will be useful in analyzing stability of both open loop and closed loop systems. The Nyquist Stability Current derived by H. Nyquist is a semi-graphical method. Like polar plot, this plot, like we have seen polar plot, this Nyquist plot is also a semi-graphical type of plot. The Nyquist plot of a loop transfer function is a graphical representation of the frequency response analysis when the frequency omega is varied from minus infinity to plus infinity. Okay, so from here we will vary the frequency from minus infinity to plus infinity, rather than from 0 to infinity, as we have done in the case of polar plot. Here we will vary the frequency from minus infinity to infinity. So Nyquist plot helps in determining the relative stability of the system in addition to the absolute stability of the system. So absolute stability simply tells us that whether the given system is stable or not, and this relative stability tells us that at how much extent our system is stable. Okay. So now we will see this from a numerical. So sketch the Nyquist plot of our system for the open loop transfer function GSHS equals to k times s minus 2 upon s plus 1 into s plus 1. So determine the range of values of k for which the system is stable. So these steps, there are some steps. So first of all, we will see that how many poles of this open loop transfer function are lying at right half of the S plane. So we can see here both the poles are lying at left half of the S plane. So you can say P defines the number of poles at right half of the S plane. So P equals to 0 as there is no open loop pole in right half of S plane. Then we will define the condition for stability. This is n equals to minus P. So n equals to, you can say 0. It means minus 1 plus j0 or critical point should not be encircled by the polar, should be encircled by the Nyquist plot, or will be encircled in such a complicated manner so that the net encirclement is basically 0. So now first we will draw the Nyquist path. So Nyquist path will be like this. There is no pole at origin. So this Nyquist path will be complete path like this. It will start from here to here and it will again cover the entire right half of S plane. And this is the radius r tends to infinity. You can see from this Nyquist path, there are 3 sections. One section is this, section 2 is this, section 3 is this. Section 2 is basically the mirror image of section 1. Okay. And section 3 is basically an origin. If you will do the analysis, you will find that this value is an origin. Okay. So now we will put s equals to j omega in this. Okay. Now we will calculate the magnitude at s equals to plus j infinity to s equals to 0. We will calculate the magnitude. So at start, we will start at plus infinity and end at omega equals to 0. So magnitude according to this expression will become 0 and 2k. 0 and 2k, if you will put the value omega equals to 0, omega equals to infinity here, then you will find this value. And angle is minus 90 and angle is 180. So the rotation is plus 270. Now we will see for this particular term how we have calculated the angle. Like term is minus 2 plus j omega. Okay, so minus 2 plus j omega will be point pole. This is minus 2 plus j omega. This is somewhat like this. Okay, so we will measure the angle from here. Okay, we will calculate the angle from here. Okay, now if this point will become reached to infinity, then this angle will become lesser and lesser. This angle will become lesser and lesser. And what happened when minus 2 plus j omega, when this omega tends to infinity, then you can say this angle is only this angle. So angle will become 90 degree. And when omega tends to 0, then this point is here. Then this point is here. So the angle will become 180 degree. And when this omega tends to infinity, then this angle will be somewhat like this. So you can say it is only 90 degree. Okay. It is written over here. Okay. And section 2 is mirror image of section 1 about real axis. So, and the section 3 is not required because it is an origin in all the cases. Okay. Now again we want to find out the point at which it will cut the negative real axis. So we will rationalize it. So for rationalization, we will multiply the conjugate values. So we have multiplied these values. We have solved out, and after solving, put this 5 minus omega square equals to 0. So the phase crossover frequency is found to be omega equals to root 5 radian per second. Now we will put this value into real part, and the real part comes to be plus k by 2. So plus k by 2 means now the Nyquist plot will cut the positive real axis, not the negative real axis. Okay. So this is the Nyquist plot, and how it is made? It is made using plus infinity, you can see here the value is 0, minus 90 and 2k, 180. 0 minus 90 is this point. 2k angle 180 is basically this point. Okay, so we will move from angle of rotation. We have calculated angle of rotation we have calculated as minus 90. Okay, angle of rotation is basically the minus 90. It is plus 270. Okay, so plus 270 means it is somewhat like this. This is the angle of rotation plus 270, and section 2 is basically the mirror image of this, and this is the origin. Okay, now for stability we have obtained the condition that n equals to minus p. It means this point minus 1 plus j0 point, minus 1 plus j0 point, where it should be lie. If it will lie here, then number of encirclement will become minus 1. But condition of for stability is that minus 1 plus j0 point should not be encircled. So it will become somewhere lying over here. Okay. So what should be the value? So this length should be length of, if this point is p, length of OP should be less than 1. We have to find out the condition for stability. And this distance is minus of 2k. Minus sign simply signifies that it is on the negative real axis. So 2k is less than 1 and k is less than 1 by 2. So for stability, k should be less than 0.5. This is how we have drawn this Nyquist plot and find out the stability. And thank you for these are the references. Thank you.